In lesson 4.1, we are going to be talking about rational functions. So a rational function is just any function that has a polynomial in the numerator and in the denominator. So we have x's in the top and bottom potentially. So we call n of x as the numerator function and d of x is the denominator function. So you've seen these before. So we have an example of one here. F of x equals 3x over x minus 1. We want to find the domain. Well, the domain is going to be all real numbers. We can plug in anything except we can't divide by 0. So we say the domain is anything except x cannot be 1. Because if you plug in 1, you'll be dividing by 0, and that's no good. So we call that number an excluded value. So our excluded value is x cannot be 1. Now, we want to see what's happening as we approach 1. We know that we can't plug 1 in, but what happens if we plug in stuff that's close to 1? So first we're going to plug in 0. Let me erase this so you can actually see it. You can use your calculator to do this. Just make sure when you do it on your calculator, you put parentheses around the numerator. But you plug in 0 and you get 0. Then you plug in 0.5. So you do 3 times 0.5 and then divide it by parentheses 0.5 minus 1. You get negative 3. We plug in 0.9 and we get negative 27. And notice I'm plugging in x values that are getting closer to 1. So I started with 0 and then 0.5 and then 0.9. I can get closer to 1 than that. I could plug in 0.99. So I'm going to go ahead and do that. It's negative 297. And then I'm going to plug in something even closer to 1, 0.999. I get negative 2,997. And we could keep doing this. I could plug in 0.9999 and 0.99999, and you get the idea. As my x values approach 1, the y values are approaching negative infinity. So what that means for the graph is I know I can't plug in 1, but as I'm plugging in things like 0, I got 0, 0. As I plugged in 0.5, I got negative 3. And then I plugged in 0.9, I got negative 27. And these just keep getting more and more negative. Now, I don't know what's happening over here. I don't really care right now. But what happens when I plug in numbers on the other side of 1? So if we approach from the right. So first, I'm going to plug in 2. So 3 times 2 divided by 2 minus 1 is going to give me 6. And I can get closer to 1 than that. So I'm going to plug in 1.5. And that gives me 9. I can get closer to 1, so I'm going to plug in 1.1. I think that gives me 33. And then if I plug in 1.01, I get 303. And 1.001, I get 3003. And I could keep doing this. I could plug in 1.0001, so on and so forth. So what's happening, so I plugged in 2 and I got 6, and I plugged in 1.5 and I got 9. And these numbers keep getting bigger. So my y values seem to be approaching infinity. Okay? And what's happening here is we have a vertical asymptote here. And you have learned about vertical asymptotes before. So the definition of a vertical asymptote, it's a line, x equals a. The mathematical definition is as you get close to that value a, your y value is approaching infinity or negative infinity, which is exactly what we saw happening in the table. Now, we can also have horizontal asymptotes. Horizontal asymptotes are when x approaches infinity or negative infinity. So horizontal asymptotes are really talking about end behavior. So as the x's get bigger and bigger, what's happening to the y values? And if it approaches a certain number, we call that a horizontal asymptote. So let's just take a look at a couple of these just using the graphs. So we've got the equations here. On this first one, vertical asymptote, it appears we have a vertical asymptote right here at x equals negative 1. And a horizontal asymptote, notice as our x's get bigger and smaller, they both seem to be approaching this number, this horizontal asymptote, which is y equals 2. All right, let's check out the next one. Vertical asymptote doesn't look like we have any, and not all functions do. Horizontal asymptote, as our x's get bigger and smaller, it looks like it's just approaching this line y equals 0. And this last one here, our vertical asymptote, definitely looks like x equals 1. Make sure you always put the x and the y since, there's a difference. And horizontal asymptote is y equals 0. So these are really easy to see just from a graph. We want to be able to find these from the equation as well. So on the next page, we see how to do that. Let's see. And right here, vertical asymptotes. The way we find vertical asymptotes, they are the zeros of dx. They're the zeros of the denominator, which we already knew that. We did that on the very first question, okay? If we wanted to find the vertical asymptote of this, we say, well, what's the excluded value? We would say that x plus 1, sorry about that, I just got really sloppy there. X plus 1 can't be 0, so x equals -1 is going to be our vertical asymptote. Same thing over here. If you set that equal to 0, you would find that your vertical asymptote is 1. So the interesting thing that happens right here is if you take this denominator, x squared plus 1, and set it equal to 0, the solutions to that are going to be imaginary. And we don't have imaginary numbers when we're graphing at this point. So that's why we say there's no vertical asymptote. Now, to find horizontal asymptotes, things get a little bit more complicated. Not a lot, just a little bit more complicated. So that's what this next table tells you on the notes. So I'm just going to erase this. We'll come back and look at these in just a second. So locating horizontal asymptotes. So we have this function, okay? It's got a polynomial on top and a polynomial on bottom. This is kind of important. The degree of the numerator is n, and the degree of the denominator is m. So that's what the n and m stand for in this. So if we have a situation where the degree of the numerator is less than the degree of the denominator, then y equals 0 is the horizontal asymptote. Now let's skip down to number 3. If the degree in the numerator is greater than the degree in the denominator, there is no horizontal asymptote. And then the third situation, well, it's the second one. If the degrees are the same, this is the horizontal asymptote. And an over bm, that's this thing right here. Okay, those are the leading coefficients. Okay, so let's jot that down. We look at the leading coefficients. So if the degrees are the same, you're going to look at the leading coefficients, and that's going to tell you the asymptotes. So back up here at the ones that we saw before. On this one, the degree of the numerator is 1, degree of the denominator is 1, and so our horizontal asymptote is from the leading coefficients. So 2 divided by 1, which is y equals 2. In the second one, the degree of the numerator is 0, because technically there's an x to the 0 there. The degree of the denominator is 2. So if the degree of the numerator is less than the degree of the denominator, y equals 0. And the exact same thing happens over here. The degree of the numerator is 0. Degree of the denominator is 2. So again, it's y equals 0. All right, so we're going to put this together and find the asymptotes of these two functions. So first we want to find vertical asymptotes. So our vertical asymptote, we're going to take the denominator and set it equal to 0. Then we'll just solve that. And we get x equals plus or minus 1. It's possible to have two vertical asymptotes. Totally fine. And then for horizontal asymptotes, we have to look at the degree. They're both degree 2, so that means the horizontal asymptote is going to be the leading coefficients, which is 5 over 1. That's supposed to be a 1. So just y equals 5. All right, this next one, vertical asymptote. We're going to take our denominator and set it equal to 0. We'll need to factor that. So we get x equals -3 and x equals -1. Once again, we have two vertical asymptotes. For our horizontal asymptote, we're going to look at the degrees. They're both degree 2, so we're going to use the leading coefficients. Our horizontal asymptote is 3 over 1, which is just 3. So that's it for lesson 4.1. It's just finding those vertical and horizontal asymptotes. In 4.2, we'll see how to use those asymptotes as the structure for our graph so that we can actually graph these entire functions.